Assalamualaikum warahmatullahi wabarakatuh. Hello, welcome everyone. Welcome to our 20th UTM Engineering Distinguished Lecture Series. Prof. Kamal should chair this session today, but unfortunately there is a technical problem just 1 minute before we start our show. So on his behalf, I will chair the session until Prof. Kamal sort out his technical glitch with the computer connection. Right. My name is Mohamed Rafiq and I am the Dean of Engineering, University Technology Malaysia. Today, it is my utmost pleasure to welcome Professor Mohamed Himdi from Université du Rennes, France. A bit about our presenter today. Mohamed Himdi received his Ph.D. degree in signal processing and telecommunications from Université du Rennes, France in 1990. Since 2003, he has been a professor with the Université du Rennes, where he was the head of the Department of High Frequency and Antennas, IETR, until 2013. He has authored or co-authored 133 journal articles and over 280 papers in conference proceedings. He has also co-authored 9 book chapters. He holds 40 patents. His research activities concern passive and active millimeter wave antennas. His research interests include the development of new architectures of antenna arrays and new three-dimensional antenna technologies. He was a laureate of the 2D National Competition for the Creation of Enterprises in Innovative Technologies in 2000 under the Ministry of Industry and Education. In March 2015, he received the JEC-AWARD at Paris on pure composite material antenna embedded into a motorhome roof for the Digital Terrestrial Television reception. So that is a biography of our speaker. Here now is Professor Mohamed Himdi from Université du Rennes with a talk entitled Reconfigurable Active Transparent Antennas. Professor Mohamed Himdi, over to you.
Okay, thank you very much, Professor Mohamed Rafiq. And thank you also for Prof. Kamal. Hope he will come later. And yes, thank you. Oh, he's here. We're happy. Prof. Kamal?
Yes.
To give me this opportunity to share with you our research especially in ITR in Rennes, especially for transparent antenna. And my talk will concern especially the reconfigurable active transparent antenna. This work was done in ITR with collaboration of many PhD students and many colleagues, especially my colleague Xavier Castel. First, allow me to show you where is Rennes. France, you see, this is the map of France. You see in the top England, Belgium, and Rennes is in the west of France, in the Brittany, this region called Brittany region. Okay, and the ITR is we are from Paris. We have with TGV 1 hour and a half. We're using the TGV high-speed train. And the distance is around 400 kilometers. And ITR is the groupment of many cities in Brittany and many institutions. It was created in 2002 between University of Rennes 1 and INSA of Rennes and a military high school in Quad-Quidon. And in 2004, Supelec joined us. And recently, in 2007, some other high school, Saint-Brieuc, in Saint-Brieuc, you can look at it here. And in 2012, many other cities and laboratory joined us, especially Polytechnique Nantes, here in the south of Brittany, and also other high school. Okay. Now, let me introduce you the outline of this presentation. I will start by to show you the context of this and the problematic of this work, and I will show you some conventional transparent conducting layers, and I will show you the limits of this technology. And after that, I will present you a new technology concerning the mesh metal film for transparent antenna. As you will see that this technology give more interesting performance, radioelectric performance compared to conventional transparent conductor layer. And I will show you briefly elaboration of electrical and optical characterization, mesh processing impacts of transparent antenna performance. And I will give you some example of transparent antenna, not specially active. And after that, I will show you some active antenna, transparent active antennas. And also some new results, not published yet, concerning the association with the agile materials, transparent agile materials with transparent antenna. The objective is to replace the component, classical component like varactor, like pin diode, like transistor. And these results are not published yet, but I will share with you. And some application of one application on transparent millimeter wave antenna. And the objective is to show you the problematic for this kind of technology in millimeter wave up to 60 gigahertz. And also the last work, not published yet. Also, it's the control of performance of the antenna, transparent antenna with optical like laser, for example. And I will conclude and give some perspective. First, the context and the problematic. The transparent antenna, our objective is to implement, to assure the implementation in state-protected city area, like historical places, or implementation on new surface, like building, car window, smartphone. Why active antenna? Active antenna is to have some, to give the antenna some agility in terms of frequency, of electronic scanning, beam shaping. Also, we are interested by flexibility of this kind of technology in order to build some conformal antenna and reconfigurable antenna for cars, for example, when it's necessary to have conformal antenna. Also, objective is to use this kind of antennas on for high rate communication, especially for millimeter wave band like 60 gigahertz, and recently for 5G especially we try to have some solution with this technology for 26 gigahertz, and also for we work hardly for to have some antennas on at 300 gigahertz. And after that, I will show you in the end of this presentation some results for optical control. And this is our objective: is with this optical control to build antenna at 300 gigahertz. Okay, just a view on some developments of wireless communication service. This is due to the expansion of antenna networks, and we have strong visual impact in urban area. Then the solution is a transparent antenna, and many researchers imagine some many years before some solution. One of them is antenna built for thin film materials. You use conductive materials with very good resistivity, like copper or any materials, but you use thin film, very thin film, in order to have transparent in the visible light spectrum. And this is what we call transparent conducting oxide, TCO films. Other kind of film is indium tin oxide, ITO, or FTO, fluorine tin oxide. This kind of materials is semiconductor. Okay, then you can, if I resume, you can use very thin metal film, or you can use semiconductor, some special semiconductor metal like ITO or FTO. And this three conventional solution, I will show you this three conventional solution based on Corning glass. This is what we call electronic glass. The dimension typically is 15 by 15, 50 by 50 millimeters, and the thickness is around 0.7 millimeter. And I will show you some ultra thin metal film and ETO and FTO solution, or mixed solution, TCO metal and TCO multilayer. Okay, here you can see some prototype with using ultra thin copper film. That's why the color is quite red, but it's transparent. You can see the logo of IETR through this thin film. And what is here, the transmission, the T is the transparency, percentage of transparency. In this case, it's not very bad, but not very high. It's around 64%. And by using 10 nanometer film, it's very thin. And unfortunately, with this solution, the resistivity, the square, ohmic square resistivity is around 8.3. It's very high, and that reduce a lot of losses. The ITO solution film with the 1 micrometer, in this case, the transparency is very good, 86%, and also the resistivity, the ohmic resistivity is bad, 8.6. And the other solution is to mix these two solutions in order to have a multi-layer solution. For example, here we use ITO, a very thin film for ITO, only 85 nanometer with the 39 micron copper, and between them in sandwich, and again ITO with the same thickness. And in this case, the resistivity of ohmic resistivity, it's become in parallel. Then you can reduce this resistivity to 4.7. But unfortunately, your transparency is reduced to, for example, here is at 60%. Here I give the slide, the figure show the transparency for what I showed you before. Okay. Now I have many slides, and I will not show all. Sorry. Yes, this is just for multi-layer. Yeah, you can show that the Corning alone is very good, but with the multi-layer, the transparency is not very good. 60%, for example. Okay. Now I want to share you with some measurements, microwave measurements for a monopole antenna. Why we use this kind of antenna? Because when you build you deposit your film, you deposit in 50 by 50 millimeter substrate, Corning glass substrate, and there are no need to have any patterning step. You use this simple to and you measure it like a monopole, like losange monopole, and very quickly you can find the performance of your thin film. And you can measure S11 matching impedance, input impedance, and the radiation pattern and the gain, as I can show you now. Here you have a comparison between many cases. First, this is the reference case in the left. This monopole is radiation resistance is around 15 ohms. Okay, this is every time I show simulation and measurements. And here we use the copper film with the thick metal, 1 micron. This is not transparent. This is opaque antenna, and it's work normal. It's working normally. And if you reduce the thickness of this film to 10 nanometer, you can see this. The input impedance is we obtain good matching, and you are very happy. But this matching is due to resistive ohmic resistance and ohmic losses. You add typically 35 or 34 ohms due to these losses. Then you can imagine your gain will be reduced. Okay. And also with the ITO film, semiconductor film, this is classical film used for many television and many smartphone as conductor. But as you can see, it's the same. The input impedance is around 45 ohms, and it's not normal. It's due to the ohmic losses, like copper film. And if you mix, in this case, the resistivity, total resistivity, including radiation and ohmic, is around 31. You improve this the performance of your antenna, but you see it's not enough, because the original one, the opaque one, is 15, and here you are at 31. But it's better to ITO and copper film, as we can see here in terms of gain. You can see here the gain for I compare with the silver, with thick silver one, 6 micron. The gain is around 2.3, but it's similar to a copper one. 2.3 dBi. This is for monopole. Normally, the monopole gain is around 5 dBi, but here we have only 2.3 because due to the limited ground plane, we use a small one. That's why we have back radiation. But anyway, it's just to compare. In the same situation, we compare this opaque antenna with the 2.3 dBi with a copper, very thin and transparent antenna using copper, and the gain become minus 5 dBi. You lose more than 7 dB. And for ITO, the same. And but for the mixed one, multi-layer solution, it's better, but you lose 4 dB too. And this is due to the ohmic losses. Okay, and also the other losses is coming from, we don't respect the skin depth. The skin depth is given by this known formula, and in this case, as I will show you just after, it's not using nanometer is not acceptable at 1 gigahertz, for example. It's okay. And here you can see for this three solution, with the first one, with opaque one, we respect the depth. With the depth, the thickness in the depth is around 2.8. That means it's very enough. We respect more than 1. We are very, very near 3, and it's very nice. In this case, the resistivity, ohmic resistivity, is around 0.002. It's very low. That's why the gain is good. But if you compare for the copper with 10 nanometer, you don't respect the with the thickness, you don't respect the depth, because you are not you are 0.002. The ratio is 0.002. It's very bad, very, very low. That means your antenna is like nothing. Okay, it's very, very small thickness, and in this case the losses is high. Also for the other solution, but and also for the last one, because we have only the ratio is only by 1 by 100. Okay. Then in the future we must be careful to use the good thickness. Okay, we must respect the skin depth, the thickness more than or near 3 times skin depth. Okay. What we propose, other solution we propose concern to improve this performance, is to use mesh metal film. Our objective is to reduce the surface losses, and in this case we increase the thickness of the conductor layer, and to reduce the ohmic losses we use the good conductor like silver. For all the prototype we use silver, because this is the best in terms of conductivity. And we can, as you can see, we will compare the first one in the left is opaque antenna, and we will compare to this mesh, and we will see the difference. Okay, and the objective is to see the performance of the antenna when we increase the metal thickness and also the aperture between two metals. And of course, keeping in mind the we must respect the skin depth. Okay. And here you can see very important results, because here we compare metal conductor opaque layer, and you see with the good thickness 1 micrometer, and the transparency is 0 because it's opaque, but the resistivity ohm square is good. Now, if we use this metal mesh with the same thickness, but with the T is the percentage of metal and non-metal part, and here we have typically 90%, and the transparency is very good, 74.5%, and the resistivity, sure, it's multiplied by 10 compared to the opaque one, but it's still it remain acceptable, very acceptable. Also, in order to respect skin depth, sometimes it's a depend on frequency. We can have more thick metal. For example, here we multiply by 3. And what we can observe that the transparency is not changed. That's very good news. And but the resistivity become better, 0.05. And also we can go to 6 micron. And also no transparency is not affected by this thickness, and we can improve the resistivity per ohm square. And this the last solution what we used in low frequency with 6 micron. But for example, for as we will see in the millimeter wave, we can reduce this thickness. Okay. Now for this metal mesh metal layer, we have many parameters to control the transparency. We have typically 2 parameters. S is the strip metal strip width, and P is the pitch. This is between 2 metal. And here you have some formula giving you the transparency versus these 2 parameters, and also the resistivity ohm square versus these two parameters. Okay. And here you have some results on transparency. Of course, if you change, you can control the transparency, the desired and acceptable transparency for you, dependent on tau. Tau is the ratio between metal and the no metal part. And here the resistivity ohm square increase by thickness, as I just showed you before. And in terms of acceptable, I tell you, it depends on what you accept as transparency. You must know that our visual acuity depend on the distance and the pitch P. Okay, the P and the theta. The acceptable theta for us, for human, is the minimum must be like this, 4.8, and this value. Okay. And for example, if you are very near, if D is equal to 30 centimeter, your pitch must be 100 micrometer. But if you accept to be at 1 meter, your pitch can be more, 300 micrometer. Okay, it depends on your application. If you are in car, for example, you are not in 1 meter, you are not in 30 centimeter, you are between. Then you can manage your pitch depending on the situation. Okay. In terms of electromagnetic wave consideration, the pitch must respect also to be very low compared to the lambda. For example, at 10 gigahertz, 3 centimeter, lambda is 3 centimeter in the air, and your pitch must be lower to this value. And for example, when we use 100 micron, no problem. And also, you must respect the skin depth losses. For example, at 10 gigahertz, we using silver, your skin depth is around 0.6 micrometer. That if you use 1 micron or 3 micron, it's no problem. But for low frequency, you must increase this depth, this thickness. And typically, we must try to respect T, the thickness of metal, superior to 3 delta. Okay. And in terms of elaboration, we of this kind of film, we use sputtering, RF sputtering technology. It's known, okay, it's not new. And in our case, we use this condition. The main sputtering parameter is per argon gas, okay, with the 30 standard centimeter, okay. And the working pressure is given here. RF power is 200 watts. Substrate target distance 80 millimeter. And substrate temperature is we use in classical temperature, is the room temperature. It is our RT is the room temperature. No need to heat. Okay. And here you can observe some photo of on the Corning glass for this this antenna with the 2 micrometer metal strip and the pitch with 300 micrometer, and it's very clean. And in order to obtain this, we must have deposit some photoresist spin coating on metal layer and export to UV light through photomask and photoresist development and the classical chemical etching of metal layer with some acid. This is classical process. No new thing. Okay, and with this, for example, for this example I give it to you, the transparency obtained is around 80%. And the resistivity is around 0.036 ohm square. It's very nice. Then in this case, you can do your antenna with no problem. As I can show you, okay, I'm going quite fast. Here you have this antenna just I showed you before at 850. And you see the radiation pattern is, you compare here, you have 4 antenna, and you see no difference between reference antenna, antenna 1, 2, 3. Okay, depending on mesh, and you see resistivity per square and different pitch. See 300, 200, 100. Typically, no difference. And also for the gain is compared to what I presented before. In this case, you can see with different pitch, the gain remain constant to 2.3, like opaque solution. And now we can go ahead for other application. Here you can see the worst case for this kind of antenna when we use a strip. If we use the strip is very thin, like for example 0.9. In terms of resistivity, ohm square resistivity, it's become very high because you added many squares. Typically here for 226 millimeter, it's like you have 29 square strip. Then you added the resistivity, okay, or resistance. For example, here your resistivity of this monopole is 29 times more than the resistivity ohm square by for 1 square. But it's not catastrophic because in terms of resistivity, in terms of ohm square, you attain 0.017 ohm square. Then it's acceptable. And you can see here with we compare this antenna and with the ITO 1, and you see this with ITO is very lossy, very lossy. Okay, but with the mesh, it's like opaque one, and it's worked very well. And also in terms of gain, here we use what is it? Yes, okay, yes, you can see the comparison of resistance, and also for gain, no difference, 4.4 dBi. Okay, here we use some big ground plane. Okay, here another antenna, large bandwidth ultra wideband antenna. You see this is a rectangular monopole, and also we obtain good results with mesh solution. Okay, sorry, I have a lot of slides. Yes, this is another one with the for broadband H-shaped slots for UMTS transparent antenna working at UMTS band. And this is in this case, this is three multi-layer antenna with the strip with the fitted by strip line technology. And so you can see it is transparent. And also here the transparent is quite good, and the resistivity ohm square is good too. And here the comparison between simulation and measurement, and the gain is around 5 dB for this antenna. And with this solution we built a big array for a base station, and it worked very well with the company called Bouygues Telecom in France. Okay, now this we can now combine this kind of antenna, transparent antenna, with active component like varactor diode here. Here you can see this is not patch antenna but slot square loop slot antenna, and fed by CPW line. And in this part, this is a bias part, okay, and with the varactor here. We use in this case the beam lead varactor because it's very small. You can see here the dimension is lower to one is lower than, yes, this is 600 micrometer by 200 micrometer, and the voltage can you can control the voltage from 2 volt to 12 volt in order to have a capacitance equivalence capacitor working from 0.8 picofarad to 0.17 picofarad. And here we use many kind of pitches. Okay, we use a smart pitch, what we call smart pitch. We change the pitch of depending on the area. For example, for the ground part, you can see we use the big pitch, 300 micron. But for you see here 300 or 500 micron, and for I zoom, yes, okay. But for the antenna part, we use 100 in order to have a good conductivity resistance in antenna parts. But for the ground, we use a big pitch in order to have good transparency. And with this for this antenna, you can see the transparency between opaque one, of course, and with different pitch, 100, 300, 1 millimeter. Okay, and in terms of transparency, it's the antenna 1 is only 66%, but the antenna 2 is 83%, and it's acceptable with 300 micron as a pitch. And in terms of what we obtain with this antenna, we obtain this at X band. We obtain agile frequency tunable antenna, working from when the voltage more from 2 volt to 12 volt. You can control your resonance frequency from 9.2 to 10.2 for 1 giga typically. And also here there's the resonance frequency between versus biasing for different pitch, and also the gain also changing. That's why the reference antenna is the best one. And for antenna 2, you can see we lose some dB, okay, but it's at this frequency it's considered as acceptable. Another solution, another example here is we use in this case the chip, the transistor on chip. This is what you see here. This is a FET transistor combined to this meander monopole. Our objective is to have a very small antenna for FM radio reception for car, for example. And here you can see the antenna. It's very hard to see it, but you can see, okay. And this is the biasing part, okay. And the pitch used here is because our low frequency at 100 megahertz, the pitch used is 360, and the metal strip is 10 micrometer, and we use 6 micron, yes, 6 micron for thickness of metal. And here you can see we use it to hear, of course, the radio, and we compare it to reference monopole. And you can see that, of course, the reference monopole quarter wavelength is better, but we continue to receive with good SNR ratio, noise ratio, signal to noise ratio, okay, value. And here you can see the matching. It's very good, very good. For reception, we need the objective is to have minus 60 dB, and it's a large bandwidth, no problem. And in terms of radiation pattern, is like a monopole, and the gain is around minus 30.8 dBi, but it's enough for FM reception. This gain is negative because the antenna is very small. It's typically lambda by 21. You can imagine it on glass, on the window glass, or okay, for the car. Another technology recently we developed in IETR with collaboration with the Chemical Institute in Rennes is transparent materials, agile materials. What we use ferroelectric one. It's called KTN. KTN. This is with the big formula. I'm not a chemist, but you can see this formula with some index here, X, and X, it's in this case 0.5, and this you have some information about critical temperature. Okay, this is some perovskite family with atomic structure in the ferroelectric states. Oh, this is, for me, it's a big word, but you have the information here, and also it's we use the same process to force by sputtering. Okay, by sputtering like a metal. But what we did in this case, we have you imagine your substrate, glass, for example. And in this case, we don't use glass, but we use sapphire. Yes, we are rich, and we deposit a cation on all the substrates on the surface, and after that we deposit the metal on all the substrate. And what after we did many antennas with this technology, and but this metal, this cation, this ferroelectric is a lossy metal, is a lossy. If not metal, is a lossy okay substrate, ferroelectric substrate. And here you can see sapphire and cation. Okay. Our chemistry, with our collaboration with chemistry lab, is to deposit this cation on all sapphire substrates. And after that, in IETR, we deposit on metal. And after that, we use laser or, of course, chemical process to design, to build our antenna. And here you can see the same example I show you at X-band with Varactor. You remember, with Varactor diode, in order to have agile tunable antenna. We use the same, but as you can see, we replace here the diode, the Varactor diode. Hope you can see Varactor diode by these materials. You see here the zoom here. You see. Of course, the first antenna, we use all the substrates or cation in the substrate, but it was very bad because it's lossy materials. But after that, we use laser cutting and we remove only in these parts. Okay, only this part, and after that we metallize and we use chemical process to build the antenna. And in this case, we as you can see here, this is the gain variation is when we change the voltage is from -2.9 to 1.7, and the losses between 3 and 6 dB due to the cation. And what you can see here, this is the antenna without cation in the red one, red curve input impedance, and with cation, you see the epsilon r is around 700, very high. And with tangent delta, very bad, 0.3. This is when you polarize this cation by yes, high voltage. Okay, I will give you the information after. And after that, if you change this voltage, if you put more voltage, your epsilon r, your permittivity decrease from 700 to 200. And also, what is the good news? That the tangent delta also is reduced, is divided by 2. That is the good news. When you apply high voltage, your tangent delta become much better. And you see here the dimension of this. Okay. And what we create, in order to polarize this cation, you must apply electric field. Okay, electric field. That means you can apply voltage between two electrodes. And here you can, the gap is around 10 micrometer. And also you must be careful, because if you want to apply high electric field, you must be careful to don't have arc. You see, not arcing. Okay, I hope this is the good word, English word. Okay. Yes, the bow. Sorry, the bow. Okay, and in our case, we limited to the maximum field is 150 kilovolts per meter, and in this case, we use 10 micrometer in order to keep the voltage, the maximum voltage, 150 volt. As I show you before with varactor, this kind of materials don't consume any electric current. It's just you apply just voltage, and your permittivity change like varactor. And here I will show you some results. As you can see here, some electrode with cation inside. You see here, the cation is inside, and between you have electrode, and the gap here is 10 micrometer. Okay, and with all this, we obtain optical transparency is around 80%. That's very nice. And also the resistance per square is around 0.224. It's not too bad. And with this pitch and this condition. And strip is 10 micrometer. And here you have a zoom, okay, for electrode. And here, this is transparency versus wavelengths in spectrum, okay, light spectrum. And here you can see that this is dissimulation with this epsilon r, with this permittivity. Then you can see that we can tune for typically 4%. It's not very much, but it is the first prototype. And you see here some results on for the voltage from 0 volt to 150 volt. Okay, it's work. This is and we compare with the opaque and transparent antenna, and you have just between you have a shift in frequency, but the tuning is working well. Here's some radiation pattern, okay. And as I see you, as I tell you, for example, the blue one, the gain is better to the red one, because at with epsilon r 200. The losses is lower. Okay, this is the gain, and it's confirmed here for the gain. Okay, and now let me show you some results on at millimeter wave at 60 gigahertz. Here at 60 gigahertz, this is another problematic, because the dimension of the antenna is very small. Here you can see the array, 2 by 4 element array. And you can tell me, oh, no need to use transparent antenna. But look at here in the left. This is not transparent antenna. This is opaque one, and you cannot see through. But if you use some, for example, I can show you 2 array. Array number one, we use the pitch is around 100. Okay. And it's not completely transparent, but you see that the ground is completely transparent, because we use more 100, typically I think 300 micrometer as a pitch. And the array number 2, what is the difference between array number 1 and array number 2? The difference is coming, this is the ID is for the array number 1, sorry. The problem is we increase the pitch for the ground plane because no antenna there. But be careful, we have a current, especially in the antenna part. And if you use the same metal pitch for antenna, your antenna has become non-transparent. You reduce the transparency a lot. But what we propose, and we just published this result. What we propose is to have the same in the ground plane, the same footprint, the same array in the ground, surrounded by ground. Of course, it's connected. It's just we modify the pitch, the machine in the ground. And as you can see here, array number 2, you have the antenna, your array, and the photo of the copy of your antenna on the ground. Okay, and it's the alignment. I will show you the influence of the alignment. You must align these two array. And in this case, in terms of transparency, it's very good. And in terms of performance, as you can see here, this is here the photo of this is voluntary. I put non-good alignment between the ground and okay. And as you can see in the ground, you have large pitch, but just in the antenna part, you have the same photo. Okay, the same design in the ground. And you can see here, it's better to see. Or in terms of results, this is the classical antenna. In terms of matching, it's very similar, not big change. And here you can see the alignment, the effects of alignment. For example, no misalignment, okay, up to 100 micrometer alignment, no big difference. That's very good news. Okay, in terms of gain, especially here, you can see in the right, you can see the opaque one, the gain reach 15 dBi, and with array number 1, the gain become very low because we lose a lot of energy in the ground plane because the pitch is very high. But when you use our solution, our proposed solution with this copy of the array in the ground plane, your gain become more interesting. Okay, we lose, of course, 2 dBi here, but 2 dB, but it's become good. Here you have some comparison. You can find this result on IEEE Access in 2019. Okay, now let me share you a new proposal with the optical control for transparent antenna. What we propose here is to, and especially for high frequency, but I will give you an example at low frequency. I'm sorry, it is just to validate the principle, but our work actually, we are working to do the same at 300 gigahertz. And what is the idea? The idea is, now your internet at home, you receive by laser fiber, okay, by fiber, optical fiber. And inside you have infrared, okay, infrared signal. And our objective here is, for example, to use a laser modulated by some information here, and this light is modulated by the signal, and we feed them. It's no contact. Okay, this laser can. You can receive it from many kilometers if you want, or millimeters or many kilometers. And in your antenna, you put some photodiode. In this photodiode converts the signal. You recuperate. Okay, you have your information. Okay, directly, and this information, of course, is modulated by high frequency. Okay, for example, information is a signal. Sinusoidal signal at, for example, 1 giga, and with some modulation, phase, frequency, magnitude, as you want. And what you receive here, S3, is your signal without, but RF signal. And this signal, you can use it to for TX antenna and to radiate it to RX antenna for one with the big distance if you want. And what we propose is to use the antenna with the transparent ground plane, and in order to let the laser pass through and to attend this photodiode. This photodiode is combined to the antenna directly in order to produce the signal directly to the antenna in order to reduce the losses. There are no RF cable. And here you can see an example. This example is very simple. It's a slot fed by a CPW line. And here you can see the biasing part with some capacitors and with some shock inductor. And the photodiode is here. It's very small. It's a beam lead, also beam lead diode. And all transparency is around 92%. And what you can see here is all dimension. I give it here. We don't publish yet this result. And yes, it's classical antenna, no new thing. And here you can see that we use some smart machine, okay, with the pitch 300 and strip with 18 micron. And the resistivity, ohm square resistivity is very good, 0.046. And the transparency is around 80%. Okay. This is the machine. I think it's okay. It's working around 1.2, 1.4 gigahertz. Well, it is classical results. No new thing. But what we did in practice, we use dual frequency laser. Okay. This is another solution. Is to use dual frequency laser and focuses by length in order to focus more. And you send this laser. You eliminate this laser, your antenna with the long range distance, and the photodiode, as I explained, it's in the antenna. And the objective is, you see, is sorry. Here you have the two frequency for laser. It's in terahertz. It's typically in 200 terahertz. It's in infrared. Okay, and in the photodiode, these two frequency is mixed in the diode because it's a nonlinear element, and you obtain the frequency at low frequency, in this case at 1.4 gigahertz, and it's worked very well. Here you can see the setup. Well, of course, in the lab we use only 1 meter, and you see here the laser part, the biasing, the photodiode biasing here, and the antenna. You cannot see it; it's very small. And here, this is a reception antenna, is the opaque one. But yes, here you can see the stability of the frequency laser versus the current. Okay, the current, the biasing diode current, and you can see it's very stable. You see the frequency is around 1.4, and you have only the fourth digit change. And here, this is what you obtain as output power in dBm compared to what we have in optical power in dBm. And we use this setup in order to transmit 64 QAM data transmission data. And here you can have the setup, and it's worked, alhamdulillah, very well. And we succeed to transmit 64 QAM modulation. Okay. And in conclusion, I show you some design and fabrication of optically transparent antenna based on micrometer mesh silver film, printed on Corning glass or in sapphire or on other glasses. And I show you also design rules in terms of line width and pitch size in order to reach high level of optically transparency, ohmic low losses, high microwave performance. Typically, what we obtain 0.60 ohm square acceptable with transparency 80-30% in the visible light spectrum. And I give you lots of example in UHF, from UHF to V band. And I show you also some active transparent antenna, and some developments are in progress, especially in millimeter wave, typically at 300 gigahertz, and combined with optoelectronic and photonic materials or components associated to transparent active. Okay. Thank you very much for your, and sorry for I was late. I take my time.
No,
Sorry.
it's okay.
Thank you.
Thank you very much, Prof. Professor Mahdi, for
What is your
information.
date?
Just now I have some technical problems here. So, okay, anyway, now we open for any Q&A session. If you have any questions, you can post to the comment section in our FB Live now. Okay, while we are waiting, to have the question from our viewers, just let me ask you one question. I think this is a very basic question. What basically, because one of the slide you show that you use the transparent antenna through your base station, right?
Yeah.
Just my question, why you need to have this transparent antenna for the
Yeah.
base station? Okay,
Yeah.
just I want to know.
Yeah. I This is this one. Yeah, this one. You mean this one? Yes.
Hmm.
Right, Prof. Kamal? This one?
Yeah. One of your slide you show that there is a base
Yeah.
station.
Yeah.
Uh,
This is the
yeah,
demand
that's
for.
right. That's right.
Yeah, this is the
Yeah.
demand. This is what the company, phone company, ask us. Okay, to
I know.
have
I know. Okay.
because for some sites, you know, it's forbidden to put any base station because it's it's visible. Okay, and as I explained in the beginning of my presentation, for example, here for some implementation on in state protected area, city area, you see, you cannot
Okay.
put for some place, you cannot, for some area you cannot put because it's not it's visible, and that's why they ask us to have this kind of antenna, but they need a base station. But some base station is around more than 1.5 meters. It's very big, with the eight
Okay.
element array with 8 elements. And this is what we this is just a prototype to show them that it's work in UMTS. But as you know, many base station work in multi-band from GSM, UMTS, and now 5G. Now they ask us to design antenna working or mini antenna in the same base station, but it's the same in the same glass in order to have base station working from 70 megahertz to 4 gigahertz or more. You see, this is for new
Okay.
generation, new generation.
Okay. All
Mm.
right. Okay. So there is one question from Muhammad Inam Abasi. Prof, please comment on the integrations of transparent antennas with solar panels or other metric structures,
Yeah.
how it will affect the performance of antennas.
Yeah, I see. Oh, thank you for this good this question. Yes, if you we of course we worked a little on this part, and you can find some paper on this suggestion, antenna combined with the metal solar. But as if you know well the solar panel, this is semiconductor like silicon, okay, and there are a lot of electrode there. You see, it's in order to collect the energy, the DC energy, and this all it's like a grid. It's like exactly what I present. Okay, antenna is meshed, and the electrode used in the solar panel is it's like what I show you in antenna. It's like a grid, many electrode. You can see many electrode, and this electrode don't affect or affect a little the performance of the antenna of the solar of the efficiency of the solar panel. Okay, and I think if you added this kind of antenna, it depends on the transparency. Because all I showed you is the transparency on the visible okay spectrum, and sure the performance will affect it, but for me it's possible to use it. My problem is not the efficiency of solar panel. My problem is the efficiency of the antenna. Why? Because the antenna will be printed in some glass, for example, and just behind you have silicon, and this silicon is high permittivity, is around 11 or 12, and with lots of losses. That means, in my opinion, in low frequency, it's very hard to use this kind of to combine antenna with this kind of substrate. But maybe in high frequency, if you can use the substrate, the glass. The glass is just a protection of your solar panel. Okay, you can use the both side of metal of glass to build your antenna. That means in the top you have your example patch antenna, and in the ground you use the ground in the glass, the bottom of glass, and you put it on your panel solar. Okay, please don't use the silicon as substrate for the antenna, because it's lossy and high permittivity. Then your antenna efficiency will become bad. Okay, this is my suggestion.
Okay, all right, thank you. We have another one question here. For 5G, which type of antenna can be used?
You can you can use in the example I give you in UMTS band. We use some kind of slots antenna, and with air gap, in order to have enough bandwidth. Okay, and to increase the bandwidth, the efficiency of the antenna. Here you can see, yes, here you can see in this slide. I will share the slide. Sorry, you see, this is three layers. One layer with slots. This is each slot shape surrounded by other slots, in order to reduce mutual coupling between antennas in array configuration. And this slot is in glass, but you have the air between the slots and the feeding part and the ground. You see, and in this case, you can have large bandwidth and high efficient antenna. Okay, of course, if you want to use some solution like patch, why not? But please use the air also, glass and air. Okay, and as you can see, for example, here it's this quite similar to the situation for the window glass. You know, the window glass is multi-layer glass. Typically, you have 2 layers or 3 layers. The objective is to reduce the noise, and also the temperature. Okay, to reduce the exchange of temperature between in and out.
Okay. All right. So we have one last question from Mama Izwan. What are the main factors to ensure that the transparent antenna has good gain and performances despite having a small size?
Oh, this is Izwan. How are you, Izwan? What are the main factors to ensure that the transparent antenna has good gain and performance despite having a small size? Typically, Izwan is not compatible. Okay, small antenna, that means you lose the gain will be reduced, and also the bandwidth will be reduced too. What I propose to you, I show you in FM solution I presented. This is to combine small antenna, but very small antenna, with active with transistor, for example. And in this case, you can have large bandwidth, very low, very reduced size antenna, and you keep your bandwidth very large, and you have some additional gain coming from the transistor. Okay, but the problem is you must it is active. You must feed. You must bias your antenna. This is active antenna, not passive. Okay, but if you accept some size reduction, please be careful for skin depth and the technology, of course.
Okay, all right. Thank you very much for Himdi. I think that is the last question.
I just added some information. If please, if you have other question, don't hesitate to send me the email or WhatsApp or anyone. Okay, you're welcome.
Sure.
You're welcome.
Yeah, sure. So maybe you can email to Prof. Himdi, or maybe you can email to I can pass over to Prof. Himdi also. It's okay, no problem. Okay, now that's the end of the session. So I pass over to Prof. our Dean of Faculty, Prof. Muhammad Rafiq Abdul Qadir.
Thank you, Prof. Kamal. And thank you again, Prof. Himdi, for accepting our invitation.
Oh,
It is
sorry, I was late. Well, I was very okay. I take my time. Sorry.
Okay, no problem. No
Okay.
problem. It is certainly a great pleasure to listen to your talk, to listen to your
Thank you very
lecture
much.
today. So, inshallah, we will meet again, either
Inshallah.
here in Malaysia or in France.
Yeah, friends, you're welcome. You're welcome.
So, thank you again. And to all our viewers, thank you for watching this webinar, Distinguished Lecture Series. We will meet
Thank you very
again
much.
next time, inshallah. So,
Thank
until
you very
then,
much.
bye-bye.
Bye bye. Thank you very much. Bye bye.